do. Here we go. I do. I have 49 passengers because it is used extensively in for airlines because they don't have time to weigh people. It would never happen, but they use estimates and they need reliable, trustworthy estimates, right? Because if it wasn't reliable and trustworthy, it could be fatal, right? Very dangerous. So this one here, though, is about the finisher times for a race in the New York. It's the New York City 10 km, 10-kilometer race. And the finishing times are normally distributed with a mean and standard deviation equal to 61 minutes and 9 minutes respectively. So 61 minutes is the mean. So what is the mean of the sampling distribution? So this is the finisher times. Let's say X is the finisher's times. So it is normal with mean 61 and standard deviation equal to 9. So question A is, what is the mean of the sampling distribution with samples of size 4? So the sampling mean is going to be normal in this case, and that's going to be equal to what? We know we can use the theorem, right? Let's use the theorem. What would mu be? Just 61, right? 61 minutes, the average time for the race, 61. And sigma is just going to be sigma over square root n. We need both. So that's going to be 9 divided by square root 4. So what do we get? What do we get? 4.5 minutes. Right. So let's try B together. What is the mean of the sampling distribution? So what is the sample mean of the sampling distribution with sizes 16? So you would just write it out the same way. X bar, if it was all possible samples, repeated sampling of the same size, but this time 16. The mean will be 61, but what will the standard deviation be? If it's all possible samples of size 16 this time. What would we put? Anyone, what should I put? Well, we want sigma over square root n. That's always the formula we use. And so sigma is sigma. It's n that's changing here. 9 over square root, this time 16. Right? N is 4 here, but n is 16 here. So it's going to be half. Notice how it's half. I'm 4 times as many samples, right? It's 4 times higher than A, right? 4 times 4 is 16, but it's half the size because it's square root. So yeah. To get what the new standard deviation is? Why does it work? It works. The theory tells it works. There's proofs for it, but a simple answer is if we don't take into consideration the sample size, then we are just defaulting to the population, and we know it can't be the same. So we know that we need to take into consideration the sample size and divide it by the square root n, and the theory tells us this is a good estimate if we use it using theory. Yeah, it's not pulled out of a hat. It's actually a mathematical, and it's been proven over and over using simulations too, like I just showed you. Yep. We know it will converge to this approximately. So if it's normal, if the population is normal, then the sampling distribution will be exactly normal as well. If the population is skewed and not anything but normal, non-normal, then the sampling distribution of the sample mean will be approximately normal. Okay, that makes sense? We can go ahead and we can answer a question. Does that help answer your question about the square root? Yep. You just want to remember to divide by square root. So now if we have those finishers, and let's say 16 are randomly selected, so this would be n right here, n equals 16. And what is the probability that their average finishing time is more than 59 minutes? So I can go the probability that the average is more. More would be this way, right? Than 59. I'm then going to take this and convert it. I'm going to convert it from an X bar to a Z. And how can I do that? With my Z score. And that's going to be 9 divided by, or we can just put it in. What was, so it sigma over square root n equaled 9 divided by square root 16, which equaled 2.25. I believe it was 2.25. So we can just put 2.25 in the denominator to make it easier. And that's going to be, actually, I can leave some room to draw there. That's going to be Z greater than that value. So what do you get for that value? Let's work on this together because this will hold in your memory for 2 weeks. I need it to stay actually even a few more weeks after that because we have a final exam in December. So let's work through that. That Z is going to turn into this. And we want to do more than. So if the mean is 61 and we want 59, then we're looking for to the right of that. Right? So we need to look that up on the table. Does anybody have a Z score here? Z score? Yep, Liam? Yeah, can we round to 8, 9? Yeah, negative 0.89, is that okay? I'm just rounding. Wasn't it 0.88888888? Yeah, so I'm just gonna round to negative 0.89. It 88, negative 88, negative 0.88 or negative 0.89 will be close on that table, right? We're going to get that on the table. We're going to do this though. Right? So it's going to be 1 minus, and we're going to look up that value on the table. Negative 0.89. Negative 0.89. Right there. 0.1867. Is that what you were looking up? That? Yeah, 0.1867. Anybody disagree with that? 0.1867 looks good. And that ends up being, what do we get? Got your calculators? You can work together through this. Yeah, 0.8133. So this is going to be 81.33%. Put that in brackets. That's why you want to round to 3 or 4 decimal places, because then you get this number a little more accurate. And yeah, that's it. So this is why we need to know the sample mean of the sampling distribution. It helps us answer questions like this. And for the airline, so this was just finisher times. We can also do the airline. Does anyone have any questions about this? Right? So instead of just randomly selecting one runner and just using a regular standard Z-score, we can then collect a group of runners and then calculate their sample average and then figure out if the average is greater than a 59, right? More than one. And it would be used here for airlines. So let's say the weights of luggage of airline passengers are normally distributed, and they would be approximately. Although with the restrictions on the rules with the luggage, I think everybody's trying to keep them at 23. If you're allowed to bring a luggage, right? You pay extra. With a mean and standard deviation equal to 20 kilograms and 3.5 kilograms respectively. So let's suppose 49 passengers are randomly selected, and what is the probability that the mean of weight of their, so the average weight, if you will, of their luggage is less than 19 kilograms. So they can actually build, the airline could actually easily build, a distribution for this and be able to know what would be safe for takeoff. They need to know the weight of the plane before they can take off. Okay, so let's do this. So we know that the luggage itself follows a normal. It's normal too, 20 and 3.5. And so we know the luggage average is going to also be normal with 20 kilograms, but the standard deviation is going to be what? So that's just the luggage, but the average luggage, what's the mean and standard deviation of the average distribution, right? Sample mean. We know that mu is 20. What would be the standard deviation? So I'll put it in full words here. It's mu is 20 and sigma over square root n, right? So sigma is 3.5 divided by the square root of 49 passengers. So we have an n here, 49. And that comes out to 0.5. So just for the distribution of luggage, this is the weights of luggage right here is just that. But the average weights of luggage, this is the average weights. That's the distribution for the average weights of luggage. But we can go ahead and use this information. We want the probability that the average for these group of passengers is less than 19 kilograms, less. Keyword less. I'll highlight it there, less. Shall stay blue. Okay, so we'll go with that. It's going to be, we'll convert that to Z using a Z score. So 19 subtract 20, divide by 0.5. And the rest we should know how to get that. So let's work on it together. Let's grab our calculators and work on this so we can figure this out. These are good questions. If you know how to do these, the next, it's very cumulative course. You'll be able to do some confidence intervals, hypothesis tests. It all builds on this using these sampling distributions. So do we have an answer for what is the Z score? There's like 40 of you in the room, 30, at least 30. There should be at least one Z score. Yeah. Let me just see. I just get a single number. Right? Z score 19, subtract 20, divide by 0.5. What do you get? -2. Yeah, I get -2. Does anybody else get -2? Good, yeah, I'm seeing some hands now. -2 would be the value. And because it's to the left, we can look that straight up. We don't need to do the 1 minus. It's already ready for us. We can just get the table. And let's grab the table. And it was -2. 0.0228. Right there. 0.0228. We'll add that in. Or that will be 2.28%. Were you giving the final answer maybe? Or no? Yeah, so did you figure it's -2, right? Yeah, so 19 subtract 20 divided by 0.5 will give us -2. We then look -2 up on the table. We don't need to do the 1 minus because it's to the left. That inequality is less than, so it's to the value area under the curve to the left, right? And then we get the table value as being 0.0228 or 2.28%. So who would use this? The airlines. They would want to know, and they always would want to keep updating this too to make sure it's always accurate. So what is the probability that the mean weight of their luggage is between 19 and 20.5 kilograms? So we know how to do this too. This would be the probability of it being between, so it's going to be X bar, not just X, but X bar. And it's going to be, we're going to standardize. We need two Z scores here now. (20.5) subtract 20, divide by 0.5. We're going to get two table values. What would be the first table value? Liam knows it. -2, all right. And what would be the second one? That's a Z. I always put a line through it so it doesn't look like a 2. Distinguishes it in case. What's the other? What's the other Z score here? What should I put in? 20.5 subtract 20 divided by 0.5 is 1. +1, right? So I'm just going to look those up. Get the table and let's look those up. So 1 happens to be right here, 0.8513. or sorry, 0.8413. And -2 we already have 0.0228. So we're going to take this value here, 0.8413, and subtract 0.0228. And we'll find the area under the curve between those two values. So 0.8413 subtract 0.0228 is going to give me 0.8185, or 81.85%. That's the probability. So really high. That would be useful information for the airline, very useful, because they can use it on averages, right? Because they don't weigh the luggage either. You don't weigh them. Although in some airports they do, right? They have to check to see what the weight is. And I don't know if they're recording it and keeping all that for the pilot to make his estimate, but I know they don't weigh people and they're estimating the people. But the luggage might be something, if you're checking the luggage, they're not weighing though our carry-on, right? They don't weigh carry-on. They just check and see if it fits. So, but it's useful information. They need it. It's important information. Right, so the last question on here is, what is the probability that the mean weight of their luggage is more than 21? So we're going to do mean weight more. There's the key word, more than 21. And that's going to be equal to the Z. Get the Z score. And find that value. So the Z score is going to be 21 subtract 20 divided by 0.5. I heard it over here. 2? 2. I see. Okay, thank you. 2. And because it's more, we do need to do 1. That's the total area under the curve. 1. Subtract the probability that Z is less than 2. And we will get the table to help us. 2 is going to be right here. Here's 2. 0.9772. 0.9772, we're going to take 1 and subtract that. And that is going to equal 0.0228, which is 2.28%. Nice. Right, because we need to get more than, we have to do the 1 minus. I grab the table for 2, just like I did. That gives me 0.9772. Take 1, subtract 0.9772. I get 0.0228, 2.28%, small percent. So the probability of the weight of their luggage being more than 21 is pretty small. More likely to be between 19 and 20.5. Okay, so it's a good application to show you how we use the sample mean of the sampling distribution. We're going to use it extensively throughout the rest of the course. We're going to use it for confidence intervals. We'll use it for our hypothesis tests, and it's used a lot. Those tests are all used in psychology too. So it's something you will see again, I'm sure, in your follow-on courses as well. Okay. So yeah, it's very handy.